Hello and welcome. Today we're going to talk about cascade control, which is very commonly applied in the process industry. In fact, more often than not, a controller would be a cascade controller. So the idea behind cascade control is you've got two process variables, PV1 and PV2, or let's say the primary process variable and the secondary process variable. They have a relationship, and regulating the secondary variable also helps regulate the primary variable. And so in cascade control, what you do is you have two controllers. The master controller, which controls the primary variable, sets the set point of a slave controller which controls the secondary variable. The slave controller, because it is controlling the secondary variable, gives indirect control of the primary variable, and any deviations in the primary variable away from set point are compensated for by the master controller. The idea is that the slave output is strongly related to the master slave output PV process variable is strongly related to the master output process variable, and thus by controlling the slave process variable you get better control of the or tighter control of the master output process variable. Here's a very common example. You got a CSTR, reactor temperature is to be controlled, and then you got a cooling jacket. This is a cooling jacket. And what you have in the cooling jacket is coolant is circulating around at a very high rate. The circulating coolant, because the circulation rate is very high, one can say that the jacket is at constant temperature. The temperature rise as the coolant flows across the jacket is not too large, and you put in fresh coolant, and the fresh coolant accumulates in a drum. The drum's level, if you're putting in more coolant in, the drum's level would rise, and in order to keep the level fixed you'll take out more overflow. So this is the overflow, coolant overflow. Okay, so the conventional way of doing temperature control would be measure the temperature and control it by adjusting the coolant flow. But in practice what is done is a cascade control system where you have a reactor temperature controller. It adjusts the set point of a slave jacket temperature controller. So this is the reactor temperature controller, and this is the jacket temperature controller. And the master reactor temperature controller sets the set point of the slave jacket temperature controller. And so you can imagine, let's say the coolant temperature goes up. Temperature of the coolant goes up. If temperature of the coolant goes up, in a conventional feedback system what will happen? Temperature of the coolant goes up, therefore the temperature, so TC goes up, therefore temperature of the jacket goes up, therefore heat transferred across the wall goes down, therefore temperature of the reactor goes up. As temperature of the reactor goes up, coolant the controller, the feedback controller here, the feedback controller says increase flow of the coolant. As flow of the coolant increases, jacket temperature decreases, and the increasing temperature of the reactor is brought back to set point. So if you look at the response would look something like this of the reactor temperature. Reactor temperature goes up and then it's brought back. Now consider the performance for the same disturbance using the cascade control system that is shown here. Notice that the reactor has a very large volume, whereas the jacket comparatively is a very small volume. So the jacket time constant would be very small compared to the reactor time constant, and therefore the slave loop, the jacket temperature control, because the jacket has a small time constant, the jacket temperature control can be very tight by the slave loop. Okay, so what happens is reactor temperature goes up, coolant temperature goes up, same thing, coolant temperature goes up, jacket temperature goes up, and in response to that, the slave controller causes flow of the coolant to go up and jacket temperature is immediately brought back, and this will be very fast because the dynamics of the jacket are much faster than the dynamics of the reactor, and so the jacket temperature will be brought back in very little time, and therefore you will see that not much effect is there on the reactor temperature. So the reactor temperature may just show just a little bit of a blip. So this is with feedback, this is with cascade. So this is a very simple example where a local disturbance gets removed by the fast action of the slave controller, and therefore the primary variable, which is the reactor temperature, remains relatively unperturbed from its position of rest. Yeah, so you get much tighter control of the primary variable because the slave loop removes local disturbances. Okay, so this is the idea behind cascade control. Here's another example. Oh, I'm sorry, I overwrote, so we will have to rub some of the stuff off. So here what we have is you want to control a distillation column, you want to control the bottoms composition by adjusting the steam to the reboiler, but it's done in a cascade arrangement. You got the steam flow controller, this is the steam flow controller, and the steam flow controller set point is cascaded down by a temperature controller, which is controlling the temperature of a sensitive tray in the column, and the temperature set point is cascaded down by a composition controller, which is controlling the bottom product purity. So you got you got three loops. At the top you got the composition controller because product purity is what you are interested in, but then product composition measurements may be very infrequent, but you still need to somehow hold the product composition, and you get indirect composition control when you hold temperature, because tray temperature, boiling temperature, is related to composition at a given pressure, and so by holding temperature you get indirect composition control, and then the composition controller, whenever you get a composition measurement, you can always make minor adjustments to the temperature set point, so that the composition, when the next measurement comes, which may be in the next shift, is closer to the is driven closer to the desired product purity. Okay, so that's that. Now, why do we use cascade control? Well, you see, you've got an inner loop. So, for example, in the reactor temperature control example, maybe I should go back. You can tune this to be really, really fast. And then the outer loop sees a somewhat faster dynamics. The outer loop then sees somewhat faster dynamics. And so, when the dynamics are faster, then you can have faster control, and therefore you can speed up the control of the primary process variable by having very tight control of the slave variable. Then we've also seen slave loop removes local disturbances. I just explained that to you by common sense for the reactor temperature control example. Here's another one. Slave loop removes local non-linearities, and the most common example is, a control valve. So you have a flow controller, and let's say, what did we have in the column example? We have a tray temperature controller adjusting the set point of the flow controller. Compare this with where the temperature controller is directly manipulating the steam flow. Yeah, so this is steam. So let's contrast these two. So hang on. I'll just do something here. So in this case, typically the valve characteristic. So if I plot steam flow of steam versus valve position, valve opening. So this is from 0 to 100%, and the flow, I guess, will also do that from 0 to 100%. Okay. Typically the characteristic of this is called the valve characteristic. The valve characteristic ideally should be linear, but more often than not it's quick opening. It's non-linear. So if you're operating here, you make the slope is low, so you make a 1% increase in the valve position, flow increases by only, let us say, 0.5%. On the other hand, if you are here, you make a 1% increase in valve position, flow increases by 1%. If you are here, you make a 1% increase in valve position, flow actually increases by 2%, 3%, 4%. So depending on where you are operating, what is your valve position, the steam flow change that you receive per unit valve position change, it has a non-linear behavior. Now in this case, what will happen? So let us say, in this case, what will happen? So let us say temperature deviates in order to, let us say the temperature of the tray decreases. So in order to increase the temperature, you'll have to put in more steam. Now if you're operating here and you make a 5% increase in steam, the steam flow actually increases only by 2.5%, and so the controller that was expecting that for 5% increase in steam I should be getting back to set point, you have not gotten back to set point, and so the controller will have to compensate for the non-linearity through feedback. So in this case, non-linearity is compensated via feedback. Compensated via feedback. Now let us consider this case, the cascade case. And by non-linearity I mean valve non-linearity. So valve non-linearity is compensated via feedback when you're using simple feedback temperature control. If you're using a cascade control system as shown here, imagine what will happen here. See, as far as the temperature controller is concerned, assuming that the flow controller is very fast, and that is very likely because flow dynamics get affected, the time constants are of half a minute maybe, whereas column tray temperature responds to a change in the valve position of the steam, the time constant may be 5 minutes, 10 minutes, because the heat exchanger or the reboiler tubes must heat up, and then more heat gets transferred, and then more vapor flows, and that vapor flow is then perceived on the control tray, and then the temperature starts to rise. So there are all these lags due to which the temperature dynamics are much slower compared to the steam flow dynamics. So on the time scale of the temperature controller, if I plot, in the cascade case, there is the flow steam, and the cascade controller output is flow steam set point, because that's the output of the temperature controller over there. And if you look at the flow of the steam averaged over the time constant of the temperature loop, which may be 5 minutes or 10 minutes, then you'll essentially get a linear relationship, because the plot would be slightly scattered, but it will essentially be linear. Whatever is the steam flow that the master temperature controller asks, this slave loop gives that flow within a minute. So on a time scale of 10 minutes, essentially whatever is the steam flow being asked by the master, the slave is delivering that. So you get essentially a linear relationship. So the slave loop, through its control action, has transformed the variability, or has transformed the nonlinearity, has removed the nonlinearity for the temperature controller. It's not that the nonlinearity has disappeared, it's just that the slave loop is compensating for the nonlinearity fast enough so that the master temperature loop doesn't see it. On the time scale of the master temperature loop, the master temperature controller sees essentially a linear relationship between whatever it's asking and the steam flow that's actually getting delivered. Okay, so the slave loop in that sense removes local nonlinearities. Cons, well, of course, in this case there's more instrumentation. You need a flow sensor, a flow controller, more instrumentation, more number of controllers to be tuned. So it's a more complex system, and there is always a complexity penalty that comes along with more complex systems. But then, you'll always find this. This is always the case. So suppose you're controlling level, you got a tank, and you want to control level. Of course, I draw it for the sake of convenience. I'll usually say, okay, level is controlled by adjusting the outflow, but in practice almost always it will be in this way. There will be a flow controller, and then the level controller sets the flow controller set point. And this is because valves are always nonlinear, and simply by the action of the flow controller removing the nonlinearity associated with the valve due to its fast control action, you get much better level control, much better, for example in this case, temperature control, anything else kind of control. So there will always be a valve and a flow controller coming together in pairs, and then there will be a master controller that is setting the set point of the flow controller. This is routine. Okay. The benefit in dynamic performance is so much that you almost always have this. Similarly, almost always it will be this way. Industrial controls will always be like this, cascade reactor control. If this would always be like this. Yeah. Okay. Tuning. How do you tune a cascade control system? Well, actually now you got, for example, two loops. Well, the tuning is very simple, inside out. Tune the innermost loop first. So in this case, for example, you'll tune this loop for a fast and snappy flow control. So if the set point changes within a couple of minutes, the flow controller gets you to set point. That's the kind of tuning that you use on this guy. And the slave loop, and once this is tuned, then you tune the outer loop. Note that the inner loop is tuned first with the outer loop off. That is, the outer loop is on manual. And then with the inner loop, once it has been tuned, you keep the inner loop on automatic, and then you go ahead and tune the outer loop. And you just keep going out in that way. So the tuning is inside out. Tune the innermost loop first with the outer loops on manual, then tune the next outer loop with inner loops on auto, and keep going out. That's the way you tune it. Please note that it is understood that inner loops, by the way, if you had looked at tuning tables, you would have found that for the same degree of oscillatoriness, a PI controller uses a lower gain compared to a P controller. So now, since we are interested in tight control of the primary variable and not the secondary variable, so typically the slave loop can be just P, because then that gives you a higher slave loop controller gain, and therefore the speed up in the slave response is more than if you were using a PI controller, and that helps faster control of the primary variable. So inner loops may be P only, so that you can have a higher controller gain for the master loop. Yeah, and that will give you tighter primary process variable control. Note that in all this, it is assumed that the slave loop is faster than the master, significantly faster than the master, and that makes sense that whatever the master asks, the slave must deliver it before the master makes the next request. Otherwise, you'll have a mismatch. Before you can deliver what has been asked, the next assignment or the next task is done. So you'll not be able to complete any of the tasks. So the slave loop dynamic speed must be much greater than the master loop dynamic speed, and I would say at least 3 times, preferably more than 5 times. So this time scale separation must be there. And you would note that, अरे भैया मैं लेक्चर दे रहा हूँ, थोड़ा सा शांति रखो. I am sorry for the interruption. So the slave loop dynamic speed must be much greater than the master loop dynamic speed, so that the slave can keep up with the requests of the master. Okay, that is when cascade control makes sense. That is when cascade control makes sense. And what else can I say? That is when cascade control makes sense. Okay. Yeah, the other thing that I wanted to say was, see, in chemical processes you have this time scale separation. So for example, if you look at a distillation column, yeah, making a change to the reboiler duty causes an change in the boil up, and the change in the boil up will cause a change in the tray temperatures immediately. Yeah. So on the other hand, whatever the change happens immediately, and let us say reflux is maintained in ratio with the distillate. In response to that, the distillate rate will change. So now there is this secondary effect. The reflux will rate will change, and the flow over the trays will change. So you see, there is the primary effect, and then there is the slow reflux effect. All right. So there is this time scale separation that naturally occurs in process systems. There are things that occur at a fast time scale, and there are things that occur at a slow time scale. Okay, so because of this time scale separation, things that move very fast and things that move really slow, cascade control is routinely employed. I mean, here, the time scale separation is there. I mean, flow changes over a few seconds. Tank residence time changes over a few minutes. So the time scale of the flow loop and the time scale of the master level loop, they're orders of magnitude apart. It is because of this time scale separation that it makes sense that you can have a slave flow loop and then the master level loop sets its set point. Okay, so this is a fundamental thing. Time scale separation is what allows the use of well, if you take a boiler, I mean, if you take a flash drum, the pressure dynamics will be very fast because you put in more steam, more vapor will boil up, and the pressure will increase. So the pressure dynamics with respect to the steam is going to be very fast, but then the composition or the temperature will change slowly because you got so much hold up in the tank. So you could have, for example, a pressure controller that's adjusting how much steam is going in, and then maybe a slow composition controller that sets the set point of this pressure controller, if that is what you wanted. By the way, this is impractical, almost never used in practice, but the point is, pressure dynamics are very fast, composition dynamics are very slow. Yeah, so again, a cascade arrangement will make sense. So this slave loop or secondary variables having much faster dynamics than primary variables occurs routinely in the process industry, and therefore the cascade loop is a routine occurrence in the industry. Okay, now cascade control can happen in two ways. Most commonly it is the series cascade, and the reactor temperature control example is an example of a series cascade. So you've got dynamics of the primary variable, the master variable, M denoting master. So U, for example, would be the coolant flow. If coolant flow changes, secondary variable would be T jacket, flow of the coolant, just so that we can relate it with the reactor temperature control example, and this would be the temperature of the reactor. So if flow of the coolant changes, jacket temperature changes, but this is very fast. The dynamics is very fast. And then as jacket temperature changes, heat gets removed across the large reactor mass or the hold up in the reactor, and therefore this is a slow transfer function. And because heat, more or less heat gets removed across the walls of the reactor, uh, that affects the reactor temperature. So this is the process, and what we do is we have the slave loop. This is the slave loop which controls the jacket temperature or the secondary variable by adjusting the available manipulated variable. The slave loop has a set point, and the primary loop or the master loop adjusts this set point in order to hold the primary variable at set point. So you got the slave controller. I will call this the slave controller. And you got the master controller. Yeah. Okay. Corona chal raha hai and I've got a cold. But I bet it's not corona. Okay, well, kahan the hum? Ha, okay, so master controller. Okay, so this is the slave loop, and this is the master loop. How do we tune it? First, this loop is off. You tune the slave loop first, tune it, and then switch this on with the slave loop on, tune this guy. Yeah, so the tuning for this block diagram would be tune the slave loop first with the master loop switched off, and then tune the master loop with the slave loop switched on. Okay, now let's derive transfer functions. What kind of transfer functions do you want to derive? So okay, for example, let us say I want to derive the transfer function between ym and ymsp. So I want to derive the transfer function ym. What is this transfer function? So if you go from here to here, you encounter this loop inside. Okay, so this loop corresponds to GCS GPS divided by 1 plus GCS GPS. So this loop corresponds to GCS GPS divided by 1 plus GCS GPS. Yeah, and so this resolves the inner loop, the slave loop. And now if you go from ym set point to ym, what you encounter in the forward path is GCM times the slave loop, which resolves to GCS GPS divided by 1 plus GCS GPS times GPM divided by, because it's a feedback loop, negative feedback loop, 1 plus whatever is in the feedback path, which is this guy, this entire guy. And if you do that, what you get is divided by 1 plus and this turns out to be okay. So that's the servo transfer function for the primary variable. What would it be for what would the transfer function be with respect to, let us say, DM या DS करते हैं, slave वाला may be more interesting. So what do? You go from here to here, from the input to the output. Numerator will be that. So the transfer function ym by ds is going to be gpm divided by this guy. One plus GCS GPS plus GCM GCS GPS GPM. Oh man. Okay. What would the transfer function with respect to dm be? It will simply be 1 divided by whatever is in the denominator. So note that the characteristic equation is the same. Whether you are looking at ym by ym set point or ym by ds or ym by dm, the denominator is going to be the same, the characteristic equation is going to be the same. Oh, okay. Yeah, so here are the transfer functions written. You also have the parallel cascade where your manipulated variable affects the secondary variable and it also affects the primary variable, but the effect is in parallel, not in series. And what you then end up doing is you have the slave loop and then you have the master loop. And what shall we do? Shall we derive the transfer function with respect to, okay, this might be slightly more complicated but not too difficult. Let's see. Which one shall we derive? Let's do the set point one first, because that's I think that's relatively straightforward, and then we'll get the characteristic equation and then we'll use that characteristic equation. Okay, so let's say we want to obtain this. So this guy will resolve to, in fact, okay, until u. Okay, so I'll do it until u. So that guy will resolve to, so u by ys set point is going to be GCS divided by 1 plus GCS GPS. That being the case, the next stage is yeah, so ym set point by y that is going to be equal to GCM GCS divided by 1 plus GCS GPS times GPM divided by the feedback 1 plus whatever is in the numerator. So GCM GCS divided by 1 plus GCS GPM times GPS times GPM, and if you solve this, it will turn out to be GCM GCS GPM divided by 1 plus GCS GPS plus GCS GCM times GPM. Note that GPS doesn't occur in the third term. And by inspection you can say, okay, whatever comes in the forward path, so that goes in the numerator, and denominator is what it is. So if I want the transfer function with respect to d sub s, what would that be? How would you do that from first principles, or using block diagram algebra? Okay, let's look at this point. Or let's look at u. So there is u change because of disturbance. So if I look at all, maybe let's look at this point. U changes because, and the change in u is GCS, because of ds, because of the action of the slave loop, is GCS divided by 1 plus GCS GPS. So you put in a disturbance, the slave loop will cause this change, okay, into u. Now when u changes by this much, you get GPM causing a change in ym, and this is fed back this is fed back how? Through GCM. Okay, so this feedback loop, how do you so there is this feedback loop. This feedback loop would be by inspection, it would be GCM GCS GPM GCM GCS GPM divided by 1 plus GCM GPS GPM. I think I'll be better off doing it in a different way. ये थोड़ा complicated हो जाता है यार. Maybe you guys are much sharper with the algebra and I'm still a dumb guy, but I'd done it in the morning. It took me a while, but अभी साला मैं confused हो गया हूँ. So let's say the slave loop is off. If the slave loop is off, then if the slave loop is off, if the master loop is off, then disturbance comes, it causes a change, and that's the kind of change that will get caused in GPM. Okay, so Ym is going to be G disturbance आया GCS into GPM divided by 1 plus GCS GPS. That's the change in Ym that I'll get because of disturbance if only the slave loop is on. Master loop is off. Okay. And this is the effect on Ym. Actually, this is minus GCS. Yeah. Okay. Now there's also a change in Ym that comes because of I think I've gotten stuck, so I won't waste time. I'll just tell you what the transfer function would be by inspection. Okay, तुम लोग derive कर लेना. Maybe we'll have a quiz on that. With respect to ds, what will it be? With respect to ds, the ym by you just go from d to ym. So it's minus gcs gpm. So it's going to be minus gcs gpm divided by this guy, the denominator here, which is 1 plus GCS GPS plus GCS GCM GPM. That's what it's going to be. Okay. These things can be derived by inspection. I'm just getting stuck with the algebra, so I won't waste time doing that. Alright. So yeah, it's derived over here. Now let's do an example. Series cascade controller design. Okay, so we've got GPS, the slave transfer function, which is much faster than the master transfer function. So what I want to do is, slave controller is P only, master controller is PI. Slave and master controllers are tuned for a closed loop damping coefficient of 0.5. Master controller tau I is chosen to cancel the dominant open loop pole. Compare performance with a simple PI controller tuned for, again, closed loop damping coefficient of 0.5. That's what we want to do. So let's design the cascade controller. For the cascade controller, we'll have to design the slave loop first. So slave loop is a P controller, so the G open loop is going to be without the Kc, s plus 1 whole cube, and the characteristic equation is 1 plus Kc times G open loop equal to 0. So that will give us s cube plus 3s square plus 3s plus 1 plus 2 Kc. That's the closed loop characteristic equation for the slave loop. So this is the closed loop characteristic equation for the slave loop. Okay, now that we have this, okay, let me do it using the root locus technique. So if I okay, the root locus would look like this. You got 3 poles at -1, s equal to -1. So yeah, this is what the root locus would look like for the slave loop. Okay, and I would like so I'm looking for a point here which subtends an angle of 60 degrees, and this should be 60 degrees. For this to be 60 degrees, this is anyway 60 degrees. So what would this guy be? Yeah, sounds like an easy equilateral triangle. So it will be what? Minus half? Okay, by inspection of the root locus, s equal to minus half plus square root 3 by 2j implies a closed loop damping coefficient of 0.5. Okay, so if you'll have a complex conjugate root, so these are the two roots, it's a third order system, there must be a third root. The third root would be s equal to, by conservation of roots, if these two roots move right, this root must move left. This root must move left, because if you remember, conservation of roots says that summation poles of the open loop transfer function is equal to summation of the roots of the closed loop characteristic equation, which has the same order as the open loop transfer function, if n minus m is greater than or equal to 2. Here n minus m is 3, so this condition is satisfied. So the other root is going to be s equal to minus half. Okay, so whatever is the other, so this will turn out to be minus 2, because the sum of the roots is minus 1 minus 1 minus 1, that's minus 3. You add these two, you get minus 1. To reach minus 3, the other root must be s equal to minus 2. So these are the three roots of the closed loop characteristic equation, and at this value of s, you can calculate Kc as absolute value of 2 over s plus 1 whole cube, s equal to s1, s1, s2, yeah, and this is s3, the third root. Okay, so just calculate the absolute value of this guy, take its inverse, that is going to be Kc, and I think this will turn out to be, you can do the algebra or we can also do it the other way. It turns out that Kc is equal to, this gives Kc is equal to half. Okay, so what do we have here? So yeah, so that's that, but real part and imaginary part equal to 0 will also give that, and since this is a third order system, it should follow a little easier here. So if I put s equal to minus a plus square root 3 aj into the equation, into the characteristic equation, what I'll get is 8 a cube minus 2 a square into 1 plus square root 3j times 3 plus 3 into a into minus 1 plus square root 3j plus 1 plus 2 kc equal to 0, and therefore what you get is 8 a cube minus 6a square minus 3a plus 1 plus 2kc. That's the real part, and the imaginary part is 3 square root 3 aj, so that turns out to be 1 minus 3 square root 3 is 2a. That's equal to 0. So the imaginary part equal to 0 gives a is equal to half. So the root that we are looking at is s is equal to minus half plus square root 3 by 2 j. That's this guy, and from here we will get kc is equal to half of 3 times a plus 6 times a square minus 8 times a cube minus 1. यार बड़ा complicated है यार ये. So half into 3 by 2 plus 6 by 4 minus 8 by 8 minus 1. So 3 by 2 plus 3 by 2 is 3. 3 minus 2 is 1. So that's equal to 1 by 2. Yeah, so kc is equal to 1 by 2 is correct. Okay, you could have also gotten it from here. So we now have the slave controller, and the slave controller kc is 0.5, a is also 0.5. Conjugate closed loop characteristic equation root pair is s equal to minus half plus minus square root 3 by 2j. By conservation of roots, the third root is s equal to minus 2, and therefore the slave loop closed slave loop is this guy. 1 plus 2 kc is 2. 1 plus 2 kc, for kc equal to half is 2, and this will factorize into these factors. Yeah, s plus 2, s plus half plus square root 3 by 2j, and s plus half minus square root 3 by 2j. Now we want to design the master controller. Okay, so we've got g closed loop slave is equal to 1 over s cube plus 3s square plus 3s plus 2, and then we will use tau I is equal to 5 minutes. That's the dominant time constant that we have to cancel it. So g controller for the master loop is going to be kc times 5s plus 1 divided by 5s, and so g open loop for the master loop is going to be, with the slave loop on automatic, is going to be kc times 5s plus 1 divided by 5s times 1 over s cube plus 3s square plus 3s plus 2 times 1 over 5s plus 1 whole cube, and this and that will cancel, we'll leave a square there. So g open loop for the master loop is going to be, without the kc, well, we'll remove the kc, okay, without the kc is going to be 1 over 5s into, let's factorize this, s plus half minus square root 3 by 2j into s plus half plus square root 3 by 2j times 5s plus 1 whole square. So this is a 1 2 3 आई ये क्या हुआ भैया? अच्छा, there is also an s plus 2 into s plus 2. Yeah. So okay, this is what we have. Okay, so this is a sixth order system, and it's got roots at s equal to 0. That's this guy. Then s equal to minus 0.2 repeated twice. Then what else? S equal to minus half plus minus square root 3 by 2j, and then s equal to minus 2. So 1 2 3 4 5 6, 6 roots. If I plot these roots on the pole 0 map, I've got this guy at the origin, then I've got minus 1 minus 2, then I've got this guy over here, minus 1 would be here, minus 0.2 would be somewhere here, so there's a there's a pole here. So 1 2 3 4, and then at minus half plus square root 3 by 2 somewhere over here, and its complex conjugate. This is the pole 0 map for the open loop master, for the open master loop transfer function. It's a sixth order system, so it will have asymptotes that are at 180 plus minus divided by 6, so that's 30 plus minus 30 degrees. Then 3 times 180 plus minus would be 90, oh, plus minus 90. Okay. Okay. So these tuck, and then 3 की जगह 5 कर दो. So 5 times 180 by 6, ये कितना होता है भाई? This would be 30. 30 times 5 is 150. So plus minus 150 degrees. Okay. So we're going to have asymptote. So okay, so locus is going to go from here to here. There'll be a break point, and you'll break out, and then you'll end up at those plus 30 and minus 30 degree asymptotes, something like this. This locus will end up at the 90 degree asymptotes. ये कुछ ऐसा जाएगा, something like this. Yeah. And this asymptote will go to 150 degree and minus 150, so something like this maybe. Yeah, that's what the root locus would look like. And now we are looking for that value of Kc for which this root, this point S, let me call this point S or S naught. S naught subtends an angle of 60 degrees. Okay, that's what we are looking for. How do we do it? Okay, if S naught lies on the root locus, see this is a sixth order system, इसमें root shoots तो निकाल नहीं सकते. So what we'll do is, if S naught lies on the root locus, it must satisfy the angle condition. If it satisfies the angle condition, then the angle subtended by pole number 1, pole number, because this is repeated twice, hmm? Hmm. Oh, this will not go like this. Understood, understood. Hang on, hang on. I made a mistake. This will go like this. ये थोड़ा यहाँ जाएगा, ये यहाँ जाएगा, and then it will break out somewhere here, and then it will go like this. Something like this. That's what it will look like. Yeah. Because this is repeated twice. This pole is repeated twice. Therefore, locus will exist here. Yeah. Doesn't matter. It still looks okay as far as the dominant branch is concerned. So we've got 2 and 3 poles here, 4 and 5 pole here, and 6th pole here. What is the angle? We'll call these angles phi, huh? So phi of 1 is going to be pi minus, because S naught must have square root, S naught must be such that its real part is square root 3 times its real part. So pi minus tan inverse square root 3. That's what it will be. Phi 2 is going to be let's see, phi 2 and 3, sorry, phi 2 and phi 3, because they are repeated, is going to be tan inverse square root 3a divided by 0.2 minus square root 3, and here I am putting S naught is equal to minus a plus square root 3aj. Yeah, so the imaginary part is this much, and the real part, ये क्या किया है, minus a ओए, हाँ, okay. Phi 4 is going to be, what's this angle going to be? ये वाला angle क्या होगा? It will be, first of all, it will be negative, and it will be negative tan inverse क्या? Square root 3 by 2 minus square root 3a divided by, it's at half, right? So half minus a. Phi 5 will be positive, and it will be tan inverse square root 3 by 2 plus square root 3a divided by half minus a, and then phi 6 will be equal to tan inverse square root 3 by square root 3a divided by 2 minus a. And then what we have is that the sum of these angles must be equal to pi, and therefore minus tan inverse square root 3 plus 2 times tan inverse square root 3a by 0.2 minus a minus tan inverse square root 3 by 2 minus square root 3a divided by half minus a plus tan inverse square root 3 by 2 plus square root 3a divided by half minus a plus tan inverse square root 3a divided by 2 minus a should be equal to 0 because the pi on the right hand side cancels with this pi. So this is a nonlinear equation in A, and you can solve this to get A. And I've solved it. I don't remember the numbers. They will follow in due course, maybe a slide later. Once we have solved it to get A, then I have my root, this guy, I have this guy, and once I have this guy, once S naught is known, Kc is quite simply absolute value of 1 by G open loop for the master loop calculated at S equal to S naught. And thus I also get the value of Kc, and therefore I have Kc and tau I. So I've done these calculations, and these calculations will be shown to you right now. So like I said, use tau I is equal to 5 minutes. That gives us a G open loop as this, and it's got these 6 open loop roots where the root at minus 1 by 5 is repeated twice. If we say that, let us say S equal to minus a plus bj satisfies the closed loop characteristic equation, the root locus, I mean I drew it in MATLAB, and the zoomed in view is, this is the zoomed in view. This is the root that we are looking for. Okay, and at this root the angle condition must be satisfied. So if this is taken as minus a plus bj, then the angle condition gives us this, and you put b is equal to square root 3a so that you get a closed loop damping coefficient of 0.5, and solve iteratively for a, gives us a is equal to 0.04504. The loop corresponding, the closed loop dominant root pair corresponding to a closed loop damping coefficient of 0.5 then is this chap, where this number is square root 3 times this number, and by magnitude condition we get Kc is equal to 0.6323. Thus our cascade controller design is with a P only controller for the slave loop. Kc for the slave loop is 0.5, for the master loop Kc is 0.6323, and tau I is 5 minutes. I also did a similar design. It's just that I took the slave loop to be a PI controller, and the slave loop was again designed for epsilon of 0.5, and tau I was taken 1 minute to cancel one of the poles, one of the slave loop poles. And if you do a similar procedure, what you get is the Kc and tau I for the master loop are as noted here. Notice that now the Kc is much lesser for the slave loop, for the master loop. Yeah, so anyway, so we're going to get dynamic responses for both these controllers, and I leave the derivation of this to all of you as an exercise. Now the next part of the problem is designing a simple feedback controller. Now to design the simple feedback controller, what we have is G open loop without the Kc in there is equal to 2 over s plus 1 whole cube times 5s plus 1 whole cube, and we are going to use a PI controller. So PI controller will have tau I is equal to 5 minutes, so 5s plus 1 divided by 5s. So that gives us a G open loop of 2 by 5s into 5s plus 1 whole square into s plus 1 whole cube. And you can see that this chap has got open loop poles at s is equal to 0, s equal to minus 1 by 5, this is repeated twice, and s equal to minus 5 minus 1, which is repeated thrice. And again, if I look at the root locus, it will have a qualitatively a similar shape. You got this guy, then you got what? Well, then you got minus 1 by 5 thrice, yeah, twice. So locus will exist here, and locus will also exist here. And then you got minus 1 thrice, so 0.2, 1, 2, 3, minus 1. Minus 1 by 5. And so again there will be the asymptotes at plus minus 30 degrees, plus minus 90 degrees, and plus minus 150 degrees. Now if I draw the root locus, कैसे जाएगा यार ये? स्ट्रेंज है भैया, ये तो ऐसे जाके ऐसे चले जाएंगे. दैट इज अंडरस्टूड. Plus 30 and minus 30, that's clear. What will happen here? So you've got one branch that went here, another branch will start going here, and you've got 3 roots here. Oh, so 3 branches, 1 2 3 और चौथी branch एक यहाँ से, तो 4 branches एक दूसरे की तरफ जाएंगी. Yeah, so it will be something like this. Something like this, and ये इधर उधर जाके ये फिर, oh, something like this is what will happen. And we are looking for this root. Okay, so this point S naught, which lies on the root locus, must satisfy the angle condition, and the angle condition is minus tan inverse square root 3, that's the angle because of this guy, plus 2 times tan inverse, where S naught is equal to minus a plus square root 3 aj plus 2 times tan inverse कितना होगा यार वो एंगल, square root 3a divided by 0.2 minus a plus 3 times, because this is repeated thrice, so its angle on this point, this is what we're talking about. This angle is going to be 3 times tan inverse what? Of course the imaginary part remains square root 3a और यहाँ पे 1 minus a. This should, actually this angle is pi minus this should be equal to pi, so pi and pi will cancel out and then you're left with this equation. It's a non-linear equation in a, and you can get a by solving this iteratively, and I've done the solution which will follow later. And once you have a, then I know that s equal to, or s naught equal to minus a plus square root 3 aj lies on root locus, and that's the point that we are looking for. At this point I get my kc as 1 by g open loop calculated, absolute value calculated at s equal to s naught, and this gives me kc, and thus I get the PI controller design with tau I is equal to 5 minutes and kc as calculated, which will follow shortly in the next slide. So so here's the root locus, yeah, and if you look at a zoomed in view, this is the root that we are looking for at 60 degrees, and at this root the angle condition must be satisfied, and the angle condition is this guy, where I have put in s naught is equal to minus a plus bj, and then we put b is equal to square root 3a so that the closed loop damping coefficient is 0.5, and solve the angle condition iteratively for a to get a is equal to as shown here. And so the closed loop dominant root pair is this guy, where this guy is square root 3 times of this guy. Okay, now that we have the dominant root pair, we can get kc using the magnitude condition, and the magnitude condition gives us a kc of 0.1368, which is actually not very large. And in this way we have completed the design of the cascade control system as well as the simple feedback control system. And then what I did was obtain the dynamic response for the slave disturbance and a set point change. So here is the servo response, and you can see this is the cascade controller with the proportional loop as a slave, and this gave us a, for this the kc was 0.6363 if you remember. The magenta line is simple feedback, the red line is cascade with a PI slave loop, and you can see the PI slave loop, the red line is only very slightly faster than the magenta line, but not noticeably faster, whereas the blue line is noticeably faster. The blue line is noticeably faster because with a P controller one is able to use a higher gain in the slave loop, and the slave loop is then faster, and because the slave loop is faster, that translates to the master loop response being faster too, noticeably faster. With a PI controller, a very high gain cannot be used because it will result in too much oscillatoriness, and that is why the red curve, which is for a PI slave loop, is only marginally faster than the simple feedback servo response, the magenta curve. Okay, then I also took out some regulator response for cascade versus simple feedback, and in this case we are changing d of s. The slave loop disturbance is changed as a unit step. The magenta curve is for simple feedback. You can see that with cascade control, the blue curve is actually much better than the magenta curve. The red curve, look at this guy over here. The red curve is looks actually much better than uh, the blue or the magenta curve, and which is basically saying that the slave loop is compensating for the disturbance pretty quickly, and because it is compensating for the disturbance pretty quickly, you see a much smaller fingerprint in the master variable response. So the fingerprint here is actually, the footprint is much smaller here. This is a large footprint, not so large, moderate footprint. This is a much smaller footprint. So by using integral action in the slave loop, we are eliminating the slave disturbance completely, and therefore we are able to achieve much tighter control of the primary variable, the master variable, the master process variable. The deviations away from set point in the master process variable are much smaller for slave disturbances. I haven't plotted the master disturbance response, the disturbance at the master variable output. The trend would be similar for a servo response. The cascade response would be much faster, whereas the cascade with PI slave loop and simple feedback PI slave loop would be similar. Yep. So that's not been shown here. But the point is, disturbance rejection, local disturbance rejection in the slave loop gives tighter primary variable control. Okay. So that's that. With this, we come to an end of this rather winding lecture. To summarize, cascade control is used when controlling a secondary fast process variable helps regulate a primary slow process variable. Set point of the slave loop is remotely set by the master loop. The slave loop is fast, the master loop is slow. The tuning is inside out, with the slave loop being tuned first and with the master loop on manual. Once the slave loop is tuned, you keep the slave loop on automatic and then tune the master loop, and in this way you keep going out, inside out tuning. The slave loop removes local disturbances, we saw that. It also removes local nonlinearities. We discussed the flow controller mitigating the valve nonlinear characteristic for the master controller. So the master controller essentially sees a linear valve characteristic, so to speak, where when the master controller says increase the flow by 5%, the slave delivers the 5% increase in flow. So it's a one-to-one, linear relationship. The slave loop also somewhat speeds up the master loop response. For the cascade scheme to work, the slave loop dynamic speed must be much greater than the master loop dynamic speed, and that is required so that the slave can keep up with the demands of the master. The cascade control system is very commonly seen in the process industry, and that is there because of time scale separation that is inherent in chemical processes. And with that, we come to the end of this lecture. Thank you for your kind attention. Hope to see you again. Thank you and goodbye.